In this video, we're going to talk about the law of sines. Before we get to the law of sines, um, the next couple of videos, we're going to talk about basically ways to solve triangles, right? So now that we know all about trigonometry, we can actually use the properties of trigonometry and these laws that we now have that we're going to talk about to actually solve triangles. Before we get there, I'm going to give a brief introduction to right triangle trigonometry. Remember, our framework for exploring trigonometry was the unit circle. Well, there's an alternate framework, which is basically where the unit circle comes from, which is right triangle trigonometry. And so, what I'm going to do is I'm going to look at the right triangle trigonometry and some of the properties of our trig functions so that we can review those and you'll have those in your belt. All right. So remember, our unit circle approach to trigonometry involves us having an angle with this terminal in standard position, which means the vertex of the angle is at the origin. We rotate the terminal side, and on our unit circle, wherever that terminal side intersects our unit circle, we have a point, and we call that x coordinate sine of that angle. Let's call this angle theta here. So sine of theta equals the y coordinate, cosine of theta equals the x coordinate, tangent of theta equals y over x. And then we can do all of our other trig functions. I'm not going to write all of those out here. But that's what we've been doing when we've been looking at right triangle unit circle trigonometry. Remember, the unit circle has a radius of 1, and so the distance from my origin to where the terminal sides intersect my unit circle, that is 1 unit long, right? This is when we have a unit circle. We can also do trigonometry when we don't have a unit circle, and this is really where right triangle trigonometry comes into play, right? So if I have my angle in standard position, it's a central angle that's intersecting in a non-unit circle, then we also want a way to be able to find out what the actual sine, cosine, and tangent of that angle are, right? If that's my angle, and I'm going to give this angle a different name actually. I'm going to call it alpha here, right? And so if I wanted to find sine of alpha, if I wanted to find cosine of alpha, if I wanted to find tangent of alpha, and we're going to have those same properties that we had with the sine, cosine, and tangent with its reciprocals, cosecant, secant, and cotangent. I'm just not going to write those here. All right. Well, this does intersect this non-unit circle, right? So this distance here is a non-unit circle. And it's going to have an x coordinate and a y coordinate as well. But what I want to do here is I want to say some things here, right? What we're going to have here is that if we drew a triangle, right? Remember, this distance is your x, this distance is your y, and this is your hypotenuse. I'm going to call it h for hypotenuse. On our unit circle, if we did that, we have this distance is x, this distance is y, and this distance is 1, right? Remember also that when we square the x plus squaring the y, we get the 1. The same thing happens here with our Pythagorean identity. X squared plus y squared is going to be equal to your hypotenuse squared, right? And so what happens here, we could almost think of these as being y over 1, this being x over 1, right? Because if I take this x and divide it by 1, I still get x. If I take this y divided by 1, I'll still have this y. Well, the same thing is going to happen here. With right triangle trigonometry, the sine of your angle is your y coordinate over your hypotenuse, right? We just didn't divide by 1 when we were dealing with the unit circle because the radius, which is the hypotenuse of this triangle, is 1. Well, when we get to right triangle trigonometry, our radius is no longer 1, it's the length of our hypotenuse. And so the sine of our angle alpha is y over h, right? Okay, x over h is going to be your cosine. And remember, tangent is sine over cosine, and so we'll still have the same actual angle because when you do that, when you divide by a fraction, you multiply by the reciprocal. So that's multiplied by x over h over x, and those h's cancel, and so we still have y over x, right? So nothing changes with the tangent, but our sine is now y over h. Our x is cosine of alpha is x over h, and our tangent is still y over x, right? So that's still equal to y over x. In in right triangle trigonometry, what we usually say is that if this is my angle theta, then we can call, instead of calling these x and y, we can call them values or words that are related to where that side length is in relation to that angle, right? So since alpha is this angle here, I know I drew that arc very quickly, but across the triangle from this angle alpha here is the side length y, right? That measures y, is y length long, right? And so since it's across the triangle, we call it the opposite side. So it's called opposite, and h is the hypotenuse of the triangle. And then cosine, since it's basically one of the side lengths that make the angle alpha, right? So the angle alpha includes your hypotenuse as one of the rays and your x as the other ray. So we call this the adjacent side, and that's the hypotenuse, right? So cosine is called the adjacent side. So cosine is adjacent over hypotenuse. And so since tangent is y over x and the y is the opposite and x is the adjacent, then we call that opposite over adjacent. All right. So this is just some things from right triangle trigonometry. It allows us to get the sine, cosine, tangent, or evaluate our trig function at angles whose hypotenuse is not equal to 1, which is always the case with our unit circle. And so with this is valuable because it helps us solve triangles that are right triangles, right? And so solving triangles, this is what I mean by solving right triangles. Whenever we solve triangles, any triangle, we're going to find the measures of sides or angles of that triangle, right? So we'll give you some given information, and using that given information, you find all the other pieces of that triangle that you don't have, right? So if I give you an angle and a side, then you can find the other angle and sides, right? That's what I mean by solving triangles. With those, we're going to use our trig ratios, right? So when I say trig ratios, what I mean is the fact that sine of an angle theta is opposite over hypotenuse, the fact that cosine of your angle theta is the adjacent side over the hypotenuse, and then that tangent of theta equals the opposite over the hypotenuse. All right. These are our trig ratios. A ratio is a division of two numbers, right? And so sine of theta is the ratio of the length of the opposite side to the length of the hypotenuse, so on and so forth. We can also use the Pythagorean identities, that sine squared of theta plus cosine squared of theta equals 1. And we got to remember that the sum of the interior angles of a triangle is 180 degrees. Now, when we're solving these right triangles or triangles in general, there's a convention in how we write our angles, right? So usually we'll use either an uppercase letter or a Greek letter to represent our angle measures, right? So uppercase A is the same thing as alpha, okay? And uppercase B, it represents the angle beta, right? So we can use an uppercase B or a beta. And then an uppercase C for angle C would be gamma. And this is how I write my gammas. If you look at print, it's a little tighter. Doesn't look like a raindrop, I guess. And then we always use a lowercase, our regular alphabet letters for our side lengths. And notice, if this is angle A, the side opposite the angle is called lowercase a, right? If this is my angle B, capital B or beta, the side opposite the triangle is side length lowercase b. And if this is gamma or capital C, the side length opposite that is our hypotenuse, and which is C, right? And so this is how we're always going to write it. So angle C is always our right triangle, and then side length C is always our hypotenuse, all right? Everything else is kind of like whichever you want to do. So it says draw and solve a right triangle in which alpha equals 60 degrees and C equals 2. Well, first I'm going to draw my right triangle. So I know I'm going to have C here, or I'm going to not say C, I'm going to do gamma because I think our textbook currently uses gamma. I might be mistaken. All right, so this is gamma. I'm going to call this side length alpha and this one beta. And this is telling me that alpha is 60 degrees, so I'm going to put that there. And the side length C is 2. All right, now with right triangles, it's important to remember that we're going to write our right triangles as C, capital C, or gamma. I'm using gamma here. All right, and we denote the right angle with the box in the corner. And so basically what I want to do is I want to find out what angle B equal, the measure of angle B. We actually know this measure of angle gamma, so that's our right angle, so that's not anything to find. But across from alpha is side length A, we need to find that, and across from beta is side length B, we need to find that, right? And so what we're going to do is we're going to think about everything that we have here. For instance, this is a 60-degree angle. This is a 90-degree angle, right? The sum of all of our angles is 180. And so what I have to do to find angle B, I'm going to find that first, or angle beta, I'm sorry, is I know that beta is going to equal. Now, you can do this two ways, right? So since this is 90, the sum of the other two angles have to be 90, right? So I can do that, the fact that it's 90 minus 60 degrees, which is 30 degrees, right? So this equals 30 degrees, all right? Now that I have that, and I'm going to put the 30 degrees in here, right? Now that I have that, I can find any other piece of information we need. For instance, I can find side length B by using my trig ratios, right? For instance, I know that since this is a 60-degree angle, and if I want to find angle A, I can use the fact that the sine of 60 degrees equals the opposite over the hypotenuse. The side opposite angle A, angle alpha is side length A. So it will equal A, and we divide that by our hypotenuse, which is 2. And so if I multiply both sides by 2, I'm going to get A equals 2 times the sine of 60 degrees. And so the sine, since this is on my unit circle, actually, the sine of 60 degrees is square root of 3 over 2. And so A equals the square root of 3 units. So I know here that A equals the square root of 3 units. And now I can find my side length. All right, I just saw that I said I was finding side length B, but I went through the process of finding side length A. All right, please excuse that. So this is side length A. Now I can find side length B. And what I'm going to do here is I'm just going to use the fact that I can use my Pythagorean identity, right? I know that A squared was the square root of 3. If I square that, plus B squared equals my hypotenuse squared, or C squared, right? Well, square root of 3 squared is 3. Plus B squared equals 4. Subtract 3 from both sides, I get 1. Take the square root, I get B equals plus or minus square root of 1. Of course, this is a triangle, so this is going to equal 1. And so side length B equals 1. All right. Now, this is an actual 30, 60, 90 degree triangle. And when we did this, we said that, oh, our 30, 60, 90 degree triangles, let's say this is 60 degrees. Well, let me put this, let me make it look like it looks here. Let's say that that's 30 degrees. And when we had a unit circle, we said that was that, this was 1/2. This was square root of 3 over 2, sorry. And this was 1/2, right? This is the 30, 60, 90 degree triangle that we reviewed when we were introducing the unit circle, right? Because it had a hypotenuse of 1. Well, this is an equivalent triangle, but it's basically just double each of the side lengths, right? And these two triangles are called similar triangles because they're proportional. Their side lengths are proportional to one another. And so a lot of times in right triangle trigonometry, they make their students, or they memorize this triangle, whereas we memorize this triangle and put it in our unit circle so that we can evaluate trig functions. All right, and so that is solving the right triangles, right? Now we're going to switch gears. Um, what we're going to do now is talk about how we solve other types of triangles. Triangles that don't have a right angle in them. All right, and this is going to be important because a lot of triangles that we deal with in real life are not right triangles. Right triangles have great properties, but not everything involves a right angle, right? And so what we're going to talk about is actually termed oblique triangles. We're going to talk about how we solve oblique triangles. And basically, oblique triangles are triangles that don't have a right angle in them, right? Some of them may have all acute angles, right? So something that looks like this, right? Where none of your angles is greater, it's equal to 90 or greater than 90. Or some triangles may have an obtuse angle. Now, an obtuse angle is an angle that's greater than 90 degrees. And so some of them may look something like that. All right, that's an example of an obtuse angle and an angle that has all acute angles. And so we're going to try to come up with methods. Well, we're not going to come up with the methods, but there are a couple of methods that we use to solve these. And one involves what we call the law of sines, and the other involves the law of cosines. Of course, as you saw at the beginning of this video, we're going to focus on the law of sines. The law of sines basically states that the ratio of the sine of an angle and the length of the side opposite the angle is the same for each angle in a triangle. All right. So I'm going to do the ratio of the sine of an angle, right? So I'm going to label this triangle here alpha, beta, and gamma, right? That means this side length here is A, this side length here is B, and this side length here is C. We have that same convention, right? Alpha is across from side length A, beta is across from side length B, and side length C is across from angle gamma, right? So basically it's saying that if I do the sine of angle alpha and I divide that by A, that's what we mean by a ratio, that's going to be the same as if I did the sine of angle beta and divide that by B, and that's going to be the same as if I did the sine of angle gamma and I divide that by C. This is our law of sines. All right. Now, what we're going to do is we're going to, and this works in any triangle, whether it's right triangle or not, it works in any and every triangle. But we definitely use these in oblique triangles, whether an obtuse triangle or in a triangle that has all acute side lengths or acute angles. I didn't label this and all that stuff like that, but it still works for acute angles, triangles with all acute angles. And so we're going to see how we can use this. Now, what we need, all right, we're going to want to use the law of sines in order to help us solve these triangles here. What we'll usually be given is 3 pieces of information, right? For instance, we might have sine of alpha, we might have the measure of angle alpha and side length alpha, but we may be missing one of these variables here for the sine of beta over B, right? But as long as we're only missing one, we can use the law of sines. And so if that is the case, we can use the law of sines, right? So these are the cases where we can use the law of sines, and we usually notate these with the S for side length and a capital A for an angle. If I'm given an angle, an included side, this is called an included side, and then another angle that makes the included side, we call this angle, side, angle. Then if we have this, we can use the law of sines, right? Because if we have 2 angles, we can find that third angle, and now we can do the sine of this angle divided by this side, and then we can choose one of these angles and do the sine of that angle by its missing side, right? We put that in our trig ratios, our sine, law of sine ratios, and we have an equation with just one variable. So angle, side, angle works for this. Angle, angle side, so we can have 2 angles and the non-included side, right? So if I were to put this S here, this will be an included side because it's included between these 2 angles here. But this is not included. We can still use the law of sines, right? Because I have this angle and its opposite side length. So I can do sine of A over S. I'm going to call that A1. And then I can use this sine, I can do this, equal that to sine of A sub 2 over its side length, which gives me an equation with just one thing that I don't have. And I can solve that equation easily using algebra. All right. Or we can be in this case where we have, okay, I know you want to do ASS, which is funny, but we're going to say side-side angle. So I have two sides and a non-included angle. And so notice here I have a side length and the angle and a side length opposite. And I have this angle here. I don't know, right? So this is like a question mark, but I do have the side opposite. So I don't know this angle, but I do know the side opposite. So I can do like sine of A over that S over there equals my sine of my question mark over this S that I'm given here. If this is A2, S2, right? So sine of A over S sub 2 equals sine of question mark over S sub 1. Now, this leads to ambiguous, this is called the ambiguous case. And the reason why it's called the ambiguous case is because we have to find an angle. Anytime you use the law of sines to find an angle, what you're going to eventually have to do is you're going to have to use your inverse trig function, right? So if I want to solve for this question mark, right, I'm going to multiply both sides by S1. I'm going to get S1 sine of A over S2 equals the sine of our question mark, right? Depending on what this equals, if this is a value that's not in the range of your sine function goes from -1 to 1, right? The range of your sine function is -1 to 1. If this number here is bigger than 1 or smaller than -1, then this triangle can't be solved. That means we don't have a triangle solution. There are 0 triangles that fit this data, this given information. All right, an alternative case is so knowing the range of the sine function is -1 to 1 will help us do this, find this value here. Another thing is the fact that if I'm going to find the question mark, I've got to find the sine inverse of this function here. I've got to do the sine inverse of this expression. The sine inverse only gives acute angles. Only gives acute angles, right? Remember our sine function, our inverse sine function gives you an angle between -π/2 and π/2. And of course, our angles aren't going to be negative here. So it's going to give you something like from 0 to π/2, which is in this quadrant here. Well, sometimes when we solve these right triangles or these oblique triangles, our triangle actually has an obtuse angle. But the sine function, the inverse sine function, will never give you an obtuse angle. And so what we'll have to do is we'll have to find the angle in the the second quadrant that has the same y value as this angle here, right? And the way we do that is the fact that these two angles are going to have the same reference angle. And so if I do 180 degrees minus that acute angle, I'll be able to find an angle in the second quadrant that has the same sine value, which is going to give us our obtuse angle, if it's possible. All right. We're going to see an example of that. This is kind of hard to for some people to wrap their heads around, but we do 180 degrees minus this initial angle, and I get this angle here that goes from 0 to that point, terminal side there. All right. Now, sometimes we get an obtuse angle and the angle is too big to make a triangle, right? Which means there is no obtuse angle that works. And if we're given an obtuse angle and we find an obtuse angle, well, we remember that the sum of the measure of the angles in the triangle is 180 degrees, then that means that doesn't work, right? And we're going to see both of these examples. So these are some of the things that we have to remember in this ambiguous case. Sometimes we're going to end up with 0, 1, or 2 solutions. And our solutions are different triangles, and we're going to see examples of that. So let's look at this first example here. And I am going to remove some of this. No, I'm not. I'm just going to keep it there. It says draw and solve the triangle which gamma equals 82 degrees, A equals 11 meters, and C equals 7 meters. I'm going to draw my oblique triangle. I'm going to draw a generic triangle. I don't know if it's acute or obtuse. All my angle, if it has an acute angle, all acute or may have at least one or at most one obtuse angle. So I have alpha, beta, and gamma. My gamma is 82 degrees. Angle or side length A, which is across from alpha, equals 11 meters. I'm going to leave the meters off. And C, which is across from gamma, is 7 meters. I'm going to leave that meters off because this is going to get messy. And this is side length B. So I have three things that I need to find: beta, alpha, and B. And so what I'm going to do is I'm going to find one of the angles first. I'm going to find angle beta. And in order for me to find, I can't find angle beta, right? Because I don't know beta or B. So I can't find angle beta. I've got to find angle alpha because I have A. I'm glad I did that. So I'm going to have to find angle alpha. And the way I'm going to do that is by doing the sine of alpha over 11, right? I have to have at least one of these, right? So if I did try to do sine of beta over B, I don't know beta or B, so I can't solve an equation with two unknowns unless I create another equation, and we don't do that, all right? And this is going to equal the sine of 82 degrees over 7, right? Now, we're going to need to use our calculators a lot in this section here. I'm going to multiply both sides by 11 because my goal is to isolate alpha. That gives me 11 sine of 82 degrees over 7. Now, I'm going to pull up my calculator, right? And one of the things you want to do, whether you have a graphing calculator or a scientific calculator, is ensure that your mode is set on degree mode, right? So if it is not, scroll down and make sure it's on degree, all right? And what I'm going to do here is I'm going to just see what 11 times the sine of 82 degrees divided by 7 equals. And that's 1.556. I'm going to write that down, 1.556. So I'm going to get sine of alpha equals 1.556. Now, we have to remember that the sine function has a range that is between -1 and 1, right? And so this is outside of the range of -1 to 1. So this is not in the range of the sine function, right? If I were to try to solve this for alpha, right, I do the sine inverse of both sides, and I get alpha equals the sine inverse of 1.556. Well, if it's not in the range of the sine function, this 1.556 is not in the domain of the sine inverse function. And so if I were to try to do the second sine inverse, I'm going to use my answer feature, second negative sign, to give you the answer, and press enter. We're going to have an error because that number is not in the domain of that function, right? And so this triangle here actually has no solution, all right? All right. And so this is that ambiguous case. Notice I had a side and a non-include angle. So we got that side and non-include angle, and we have an ambiguous case, right? And so let's look at, I'm actually going to skip this example here in our notes because I want to tell you about some other stuff. This is going to take a very long time to complete. So we're going to do this face to face. And so I'm going to go to the next ideas that I have just to get you started with some of the applications. So once we know how to solve these triangles using our law of sines, and we'll get more practice with that, you should probably look at your homework on the online system before you get to class. It says using trigonometry, we can find the size of an object without measuring the object, but by measuring an angle, right? And then doing some trigonometry. And so we have two things here: an angle of elevation. Sometimes they call it an angle of inclination. Inclination. All right. Angle of elevation alpha for a point above a horizontal line is the angle formed by the horizontal line and the observer's line of sight through the point. And so the way I like to explain this is think about you as a person. I'm going to draw a person. It's going to be a stick figure. You have eyes, right? And wherever your eye is, there is a horizontal, right? Parallel to the ground, if the ground is horizontal. And say you're looking up at a plane in the sky. So we have this plane here. And you're looking up at that sky, right? The angle of elevation is the angle formed from this horizontal. This is the horizontal. And your line of sight to the object. This is your line of sight. All right. And so it's this angle here. This angle is your angle of elevation. We also have an angle of depression. The angle of depression, beta, for a point below a horizontal line is the angle formed by the horizontal line and the observer's line of sight through the point, right? So instead of looking up, in this case, we're going to be looking down. So let's say that we're in an apartment building downtown somewhere or a condo downtown on vacation after COVID's over. And we have some balconies here. And let's say that you're sitting on this balcony on some chair, right? And then you see someone walking a dog. Okay, I don't know how to draw a dog. Or some animal, right? So from your eyesight, there's the horizontal, right? So from your eyesight, there's the horizontal. And so if you're looking down at the dog, then this is your line of sight. And your angle of depression, beta, is the angle made between the horizontal and your line of sight. All right. So this is your angle beta. So these are two applications that we may use in order to help us solve problems. There are also some applications in air navigation or in navigation in general, right? With something known as a bearing. The bearing is the measure of an angle that describes the direction of a ray. The measure of an angle that describes the direction of a ray. So in air navigation, a bearing is given as a non-negative angle that's less than 360 degrees, that's measured in a clockwise direction from a ray pointing due north, right? And so what we're going to do is I'm going to go ahead and do this example here. It says draw the ray indicating the direction of a plane that's traveling with a bearing of 35 degrees. And so my bearing is always going to be an angle that's drawn in a clockwise. I know we normally draw angles counterclockwise, but a bearing is always drawn clockwise from your ray that's pointing due north. So this angle here is, or this ray here is pointing due north, and I'm going to draw an angle that's 35 degrees that's drawn in a clockwise manner because we want to draw an angle that has a bearing of 35 degrees. So from my north facing ray, I'm going to draw a 35-degree angle in a clockwise manner. And so this is the direction of the plane. Okay. In marine navigation and surveying, the bearing is the acute angle the ray makes with the north-south line, including the directions, right? And so if we think about a compass with its directions, we have north, south, west, and east, right? And the way I remember west and east, wow. I create the word we, right? Sometimes people get east and west mixed up. W-E, we, there we go. We, W is on the left, E is on the right. So in marine navigation, we give you two letters here, right? I have south and east, for instance, and I have a 45-degree angle, right? And so when we draw the acute angle, it's always going to be an acute angle that is made with the north-south line, right? And we're going to tell you whether it's drawn from the north line or the south line, and then we'll tell you which side of the north line or north-south line to draw that angle, right? For instance, it says draw the rate indicating the direction of a ship traveling S 45 degrees east, right? This reads 45 degrees east of, and then I'm just going to say south. Okay, so my south is here pointing downward. I'm going to be 45 degrees on the east side of the south line, right? And it's going to be an acute angle. So I'm going to go 45 degrees in that direction on the east side. And this, if that was a straight line, would be the direction that that ship is traveling. All right, I'm going to stop this video here. We're going to actually fill in the rest of our notes face to face or when we meet synchronously. And so I'll see you in class, or I'll see you next time.